In episode 75, titled Roaming Behavior, Sticky Clients, Disassociation, and User Impact, the focus is on roaming as a client choice that is influenced by network settings but never fully controlled by the infrastructure. Wireless roaming is often described as if the network moves a client, yet in practice, the client device decides when to leave one access point and join another. The network can encourage good decisions through radio design, power tuning, and roaming assistance features, but it cannot force every client to behave perfectly. The exam tests roaming because many user complaints in offices and campuses stem from poor roaming decisions, leading to slow performance, dropped calls, and confusing intermittent connectivity. When you understand sticky clients and disassociation events, you can interpret user experience problems as roaming and RF design issues rather than as general bandwidth shortages. Roaming also depends on authentication behavior, because even a perfectly timed handoff feels like a failure if re-authentication takes too long. The goal is to connect roaming mechanics to user impact in a way that lets you choose practical tuning actions. This episode builds a coherent view of how roaming happens, what breaks it, and what tuning steps improve it. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Sticky clients are devices that hold on to a weak access point longer than they should, and the result is slow performance even when a stronger access point is nearby. Clients make roaming decisions based on their own algorithms, which may prioritize avoiding disruptions over seeking the best signal. That means a client may remain connected to an access point with poor signal-to-noise ratio simply because it is still connected and because the client wants to avoid the risk of roaming. As the client moves away, the link quality degrades, modulation rates drop, retransmissions increase, and the user sees slow speeds and high latency. This is frustrating because the infrastructure may have excellent coverage and capacity, yet the user experience is limited by a client clinging to the wrong access point. The exam tests this by describing scenarios where users in motion experience slow connectivity while stationary users are fine, which often points to sticky behavior. Sticky clients also reduce overall efficiency because they consume airtime at low rates, which can degrade performance for other clients sharing the channel. When you recognize sticky behavior, you stop chasing bandwidth and start focusing on RF boundaries and roaming incentives. Disassociation events are the moments when a client drops from an access point, and they can drop sessions in ways that are especially damaging to real-time applications. Disassociation can occur because the access point, or the client, decides to end the association, because signal quality falls below thresholds, or because a roaming transition triggers a disconnect before a new association is stable. When disassociation occurs, any in-flight traffic is interrupted and applications may need to reconnect, re-authenticate, or rebuild sessions. For web browsing, this may be a minor annoyance, but for voice and video calls, it can be disruptive, causing audible glitches or full call drops. The exam often uses real-time app impact to emphasize that wireless reliability is about continuity as much as about throughput. Disassociation can also trigger re-authentication, which can add delay and make the interruption longer than it needs to be. In dense environments, repeated disassociation events can look like unstable coverage even when signal levels are acceptable, because the issue is not coverage but roaming transition quality. Understanding disassociation helps you interpret user complaints about walking and talking, where the act of movement triggers the failures. Roaming assistance features exist to improve transitions and reduce sticky behavior, but they require careful tuning because aggressive settings can cause unnecessary disconnects. Assistance features can include mechanisms that encourage clients to roam, share neighbor information, or enforce minimum signal thresholds that prevent clients from staying connected when link quality is poor. The purpose is to make roaming faster and to keep clients on access points that can serve them efficiently. The risk is that if thresholds are set too high, or if assistance is applied without considering client diversity, clients can be pushed off access points prematurely, leading to frequent disassociation and poor experience. Tuning matters because different environments have different cell sizes, different interference patterns, and different client device behaviors, and a setting that improves roaming in one site can worsen it in another. The exam expects you to recognize that roaming features are tools, not magic, and that they must be aligned with RF design and client mix. Assistance is also most effective when access point placement and channel planning are already solid, because no amount of tuning can fix a fundamentally poor RF layout. When you treat roaming assistance as an amplifier of good design rather than as a replacement for it, your solutions become more reliable. Aligning transmit power and channel plan is one of the most important actions because it shapes cell boundaries and influences when clients decide to roam. If transmit power is too high, access points create large overlapping cells, and clients can hear a distant access point well enough to cling to it, increasing sticky behavior. If transmit power is too low, coverage holes appear, and clients may drop before finding a stable new access point, increasing disassociation events. A well-aligned power plan creates predictable overlap that supports roaming, where a client moving away from one access point naturally sees a stronger neighbor without large dead zones. Channel planning matters because if adjacent access points share the same channel unnecessarily, co-channel contention can delay transmissions and make roaming decisions less stable. A clean channel plan reduces interference and makes signal measurements more meaningful to clients, improving roaming behavior. The exam often tests this by presenting scenarios where roaming is poor and expecting you to consider RF planning rather than only controller settings. Power and channel alignment is also a consistency issue because uneven power across access points can create roaming traps and coverage shadows. When you tune power and channels deliberately, you are shaping the environment that client algorithms respond to. Authentication delay is another major contributor to roaming problems because even a fast physical transition feels slow if the client must perform a full authentication exchange at each handoff. Authentication delays can be caused by complex security modes, slow identity infrastructure, or configuration that forces full re-authentication too often. Fast transitions improve handoffs by reducing the time it takes for a client to become fully authorized and able to pass traffic after joining a new access point. In enterprise environments, this is especially important for voice handsets and mobile devices that move while maintaining real-time sessions. The exam expects you to connect call drops and roaming failures to authentication delays as well as to RF issues, because many roaming failures are not about losing signal, but about spending too long in a partially connected state. Fast transition capability must be supported by both the network and the client devices, which means compatibility and configuration consistency matter. If fast transitions are available and tuned correctly, roaming becomes less noticeable to users because the interruption window shrinks. When you ignore authentication delays, you may fix RF coverage and still see dropped calls because the handoff authorization takes too long. A common scenario is calls dropping while walking through a hallway, which is a classic indicator that roaming handoffs are not smooth enough for real-time voice. Hallways often have linear geometry and can create coverage patterns where clients move quickly through overlapping cells, making roaming decisions frequent. If access point placement or antenna choices create uneven overlap, a client may lose quality rapidly and disassociate before it completes a new association. If authentication transitions are slow, the client may connect to the new access point but fail to pass traffic quickly enough, causing the call application to drop. This scenario often appears in environments with voice-over Wi-Fi handsets or mobile conferencing where movement is normal. The exam expects you to interpret hallway call drops as a roaming and RF boundary problem, not merely as a bandwidth shortage. Correct reasoning considers whether access points are spaced appropriately, whether transmit power is aligned, whether channels are planned to reduce contention, and whether fast transitions are enabled and compatible. It also considers whether the hallway is affected by obstacles or reflective surfaces that cause signal fluctuations. When you treat the hallway as a roaming stress test, you can design for continuity instead of hoping coverage alone will be sufficient. Uneven access point power is a pitfall because it creates roaming black holes where clients cling to a loud access point even when they are physically closer to a quieter one. If one access point transmits at higher power than its neighbors, its signal may dominate over a larger area, causing clients to remain associated with it far beyond its ideal cell boundary. Meanwhile, the neighbor access points may not appear stronger enough to trigger a roam, so the client stays on the wrong access point with poor link quality. This also creates load imbalance because many clients may remain attached to the loud access point, overloading it while nearby access points remain underutilized. The exam tests this because it is a common misconfiguration, especially when access points are deployed over time and power settings are not standardized. Uneven power also complicates troubleshooting because coverage maps can look good while roaming behavior remains poor. Correct practice is to standardize power settings and adjust them in a coordinated way based on environment and density, rather than allowing outliers. When you eliminate power outliers, you create more predictable roaming incentives. Excessive channel changes are another pitfall because they confuse clients and can cause drops, especially if the environment shifts channels frequently during operation. Channel changes can occur through automatic channel selection systems that respond to perceived interference. But frequent changes can disrupt clients because their association and scanning behavior depends on stable channel availability. When an access point changes channel, clients may lose connection temporarily and must scan to find the network again, creating disassociation events and user-visible disruption. In environments with real-time applications, even brief channel-induced disruptions can drop calls or cause major quality issues. The exam expects you to recognize that automatic channel behavior must be managed, especially in dense deployments, because instability is worse than suboptimal channel assignment. Excessive channel changes can also indicate that the environment is noisy or that channel planning is poor, causing the system to chase interference rather than settle. A stable channel plan with controlled adjustments is often better than constant automated retuning. When you see roaming issues paired with channel changes, you should consider whether channel management is causing unnecessary client disruption. Quick wins include measuring roam events and tuning thresholds gradually, because roaming improvements require evidence and careful iteration rather than aggressive changes. Measuring roam events gives you visibility into how often clients roam, how long handoffs take, and whether failures correlate with specific access points or locations. Gradual tuning means adjusting power, thresholds, and assistance settings in small steps and observing the effect, reducing the risk of pushing clients into excessive disassociation. This approach respects client diversity because different devices respond differently to the same RF environment, and a sudden aggressive change may fix one device type while breaking another. The exam expects you to treat tuning as a controlled process because roaming is a complex interaction between infrastructure and client behavior. Quick wins also include reviewing channel stability and ensuring that the environment is not changing channels too often, because stable RF conditions support stable roaming. By measuring and tuning slowly, you improve experience while maintaining predictability. When you can explain why gradual tuning is safer, you demonstrate practical operational judgment. Operationally, updating client drivers and device profiles when possible can materially improve roaming behavior because many roaming decisions and fast transition capabilities depend on client software. Client devices contain the roaming algorithms, and older drivers may handle roaming poorly, scan inefficiently, or fail to support certain transition optimizations. Enterprise environments often manage device profiles through mobile device management or endpoint management tools, which can enforce consistent wireless settings and keep drivers current. While you cannot control every guest device, you can often improve the experience for managed devices, which can reduce support burden and improve overall perception of the wireless network. The exam expects you to recognize that not all roaming issues are solved by changing the network, because sometimes the client is the limiting factor. Updating clients also improves security because newer drivers often include fixes for encryption and authentication behavior. Device profiles can also control preferred bands and network selection behavior, reducing the chance of clients clinging to congested bands. When you include client maintenance as part of the solution, you show a complete view of roaming as an ecosystem problem. A useful memory anchor is roam depends on power, channels, auth, thresholds, because it captures the levers that influence client decisions and handoff quality. Power shapes cell size and overlap, influencing whether clients see a stronger neighbor and when they decide to roam. Channels determine interference and contention, which affect link quality and the stability of the RF environment clients evaluate. Authentication determines how quickly a client can become fully connected after roaming, and delays here can cause call drops even when signal is fine. Thresholds represent the roaming assistance and minimum signal policies that encourage or force clients to move, and they must be tuned carefully to avoid unnecessary disconnects. This anchor helps you diagnose symptoms by checking each lever systematically rather than guessing. It also helps you plan changes because you can decide which lever is most likely responsible based on the symptom pattern. When you apply the anchor, roaming becomes a manageable tuning problem rather than a mysterious user complaint. To diagnose sticky client symptoms and propose fixes, look for patterns where users have strong access point density yet experience slow performance while moving, often improving when they stop or when they manually toggle Wi-Fi. Sticky behavior often appears as devices remaining connected to a distant access point with low signal-to-noise ratio even though a closer access point is available, which can be inferred from client association logs and observed signal metrics. Fixes typically involve reducing excessive transmit power that creates oversized cells, aligning power levels across access points to remove outliers, and improving channel planning to reduce contention that delays roaming decisions. You also consider roaming assistance thresholds, ensuring they encourage clients to leave weak connections without pushing them off too aggressively. If disassociation events are frequent, you examine channel stability and authentication performance because unstable channels and slow authentication transitions can cause drops during roaming. You also evaluate whether fast transitions are enabled and supported by the client population, because reducing authentication delay improves real-time app continuity. The exam expects you to propose fixes that address the underlying cause rather than simply adding more access points. When you connect symptoms to power, channels, and authentication, your fixes become coherent and defensible. To close episode 75, titled Roaming Behavior, Sticky Clients, Disassociation, and User Impact, the key is that roaming is driven by client decisions shaped by the RF environment and by authentication behavior, and user impact is most severe when real-time apps are interrupted. Sticky clients cling to weak access points and slow down performance, while disassociation events interrupt sessions and can drop calls and video meetings during movement. Roaming assistance features can help but must be tuned carefully, and the most effective improvements often come from aligning transmit power and channel planning so overlap is healthy and contention is reduced. Authentication delays are a major contributor to poor handoffs, and fast transitions reduce disruption when supported and configured correctly. Common pitfalls include uneven access point power that creates roaming black holes and excessive channel changes that confuse clients and trigger drops. Quick wins like measuring roam events and tuning thresholds gradually improve outcomes while avoiding new instability, and updating client drivers and profiles can improve roaming algorithms and compatibility. The memory anchor that roaming depends on power, channels, authentication, and thresholds provides a reliable troubleshooting sequence. Your rehearsal assignment is a roaming story rehearsal where you narrate a user walking through a space, explain what the client sees, what triggers the roam, how authentication completes, and what tuning change would reduce call drops, because that narration is how you demonstrate roaming understanding the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.